correct a little bit what my speaker before said. He said, I am the animateur of working group 14. That is not right anymore. I stepped down from that position earlier this year, so I am proud to see here the vice animateur, the current one. That is Karin Beppler. She succeeded in the ranking, and so I am at the moment without any official ITA function standing here in front of you. I was asked to give a presentation about phase support and ground improvements. I would like to give you, in the first part, a little bit about the phase support models, how to, let's say, to assess the required phase support pressure. I would later on give you a short introduction into some practical hints how to maintain phase support pressure at your tunnel. And then as well, as in most soft ground tunnels, there's always an occasion when you lose your phase support. And so what to do during that time and how to actually recover controlled working conditions once you have had even a phase collapse. So it's a little bit a different approach, but I hope it will be clear enough for you to follow that. And please, we are now sitting here together for another 1.5 hours. If you have questions in between, just raise your hand, and then we can even, if I can answer it right away. So the first question is, why do we need active phase support in TBMs? Why do we need to have an active pressure inside the excavation chamber? It's not an invention of the engineering companies to punish contractors. It actually has some purpose. The first one is we want to minimize the settlements on the surface with that, and thus preventing sinkholes. The other advantage is we're using active phase support is we want to have with that a stabilized tunnel face in the front, so your excavation process is operating in a constant and a controlled mode. Another thing is, when you have finally passed with your TBM, you want to erect your segmental lining in the back of the TBM. That's what you want to do in, if possible as well, in a controlled environment. So the geometry of your hole which you excavated should be hopefully very constant. And to facilitate that, you need to have a complete active phase support here in the front with controlled excavation volumes, and then you have as well a more or less controlled geometry in the back where you erect your lining in and where you can backfill then the tail void behind the TBM. And last but not least, if you have made a controlled excavation during advance, you have as well the possibility to have a controlled intervention, because your tunnel phase is stable, you have the same conditions, more or less the same conditions as it have been in situ, and so you know what you are expecting. So everything is in a more controlled matter, and actually it doesn't hurt to have some phase support pressure in the front. The TBM doesn't mind. The technology is strong enough to do it, so it just doesn't is of advantage for the whole tunneling process. How much loads do we need? So what are the acting loads in the tunnel operation? We have here as one of the dominant pressures is the water pressure, which is acting from the measurable groundwater table. You have the earth pressure from the top going down to your level here. And then you have as well from the operation, because no operation is constant, so you have a certain fluctuations. So you have an additional factor which you put in. Typically it is plus minus 0.1 bar for slurry TBM operation, or plus minus 0.3 bar for EPB TBM operations. So that is defining the required pressure, and you are practically then counteracting. You're building up this pressure inside the excavation chamber, and here indicated with that. So you have here then the counter force practically stabilizing the tunnel face in the front. There's a little equation here, and you can see we have partial safety factors. So we have the water pressure, which is easy to measure, and you then place as well a safety factor there on top. As the same with the earth pressure, you have there a partial safety factor as well, which you place in front. So you have, let's say, one safety, another safety, and then you have here this operation pressure as well as another safety factor. In shallow tunnels, it is, you have not only a problem when you have the pressure too low, you can have as well a problem when you have the pressure too high, because then you act very strong, and you can, even in shallow soft soils, you can act and have heaves on the surface. So it's quite a good idea to give a little thought on the face support calculations before you start with a tunnel operation. Here's just an example just to visualize what happens when the face support pressure is too low. You see how nice and local the settlement develops slowly from the TBM, the simulated TBM, and how it just goes up and straight up. Of course, this is in beautiful sand, cohesionless sand. You have different conditions mostly on your projects, but the effects are more or less the same. So how do I apply this additional face support pressure? As I explained before, we have inside the excavation chamber, due to the safety factors, we have a higher pressure than outside. If I would do it just with let's say with water, and have fill in a slurry TBM, the excavation chamber full of water, it would not help, because the water would just disappear and gone. And you cannot build up a active face support pressure. So we use, therefore, a bentonite slurry. We pump it in, as already presented to you this morning, and this, actually, the bentonite slurry tries to penetrate as well into the ground. The water particles will go and disappear into the ground, but it will build up a filter cake, which you can see here on the tunnel face, which then finally seals the tunnel face, and that's the point when you actually can apply additional pressure onto your tunnel face. You see here as well, just by this example, the scraper here, one of the tools, and you can see here as well as it plows along the tunnel face that it is always destroyed. It is a continuous refreshing practically of your filter cake, of your membrane on the tunnel face. For EPB TBMs, it's a little bit difficult or complicated or not, as you will like. You have there the possibility and the requirement. You have to create practically the mixture, toothpaste-like mixture inside your excavation chamber, which is typically around 60% of your excavated material, 40% of conditioning foam. Both together are working very nice, as I said, like a toothpaste. And that moment, you can then actually, with this, let's say, heavy material, you can apply as well additional face support pressure onto your tunnel face with this excavated material itself. Instead of, let's say, the bentonite and the slurry suspension, here with an EPB, you use practically the foam conditioning, what you have to do, and to use it together with the excavated material. Good. Starting with the calculation of the face support, the assessments, it was starting already in the late 1900s. As you can see here is a sketch of observations of engineer Forchheimer, who did as well research work on that with colored sand. And you can see in the 130 years, it looks more or less the same as it was in the video I just showed you before. So no new developments in geology in 130 years. The geology is still the same. So, but how do we calculate? We have the possibilities to use the at-rest pressure for face support calculation. But at the end, it will turn out here with the horizontal pressure acting onto the TBM, onto the tunnel face, it is ends up mostly in very high pressures, comparably high pressures. We can use the active earth pressure, which is in a two-dimensional failure case. Here again, you are using practically the full height of the till the surface, and it's more like a retaining wall system. And here you get somehow smaller values, but still something which you not really need to do. With the introduction then of 3D modeling, we had then the first 3D models which had an arching effect in the horizontal plane. That was like in diaphragm walls used quite a lot, and it was transferred into the tunneling. You see here the tunnel face, and then you have here your arching model right on top. But it goes all the way up to the surface as well, and thus creating, especially when in deep tunnels, still quite high values for your face support. So the most commonly used models we are used now do not have a horizontal. They have in the horizontal plane a normal sliding wedge, which is according to your tunnel profile, but on top you use there as well a vertical arching model, so you practically reduce the influence of the overburden up to 1.5 diameters, and then at one point it is negligible than the depth. So this way you do not reach into very high pressures when you have a large overburden. So the assessment of the face support has been done. Then you somehow have to apply that. Most models are lower limit equilibrium models. The reduction of the earth pressure below the at-rest state will practically define then that you allow movement and you allow settlements, small settlements, otherwise you cannot activate it. And then no model actually requires to make use of the lower pressure limits. It is important as well to go to the higher limits to look, as I mentioned before, especially in shallow tunnels, to look at the higher limits. Where are my most highest pressure the overburden can take before you end up with blowouts and heaves. So once you have made your, so you have assessed the required face support pressure, you have actually to go and look for a slurry TBM. How do I apply this face support pressure? And so you have to adjust the bentonite suspension to your geology. And that is something you do with a grain size distribution curve. You practically take the D10 value here out of the grain size distribution curve for each geology, and then you transfer it into the required shear strength of your bentonite suspension. That said, okay, you have one of the key performance indicators, which we call like that, which you adjust your slurry suspension to. But you have, of course, during the excavation, you have to monitor as well that. And you have to control that the suspension you're using, it's a kind of a consumable. It wears down, it loses the strength. So you have actually to monitor in regular instances the quality of your bentonite suspension. And not like once a week or something like once a month. That must be frequent, at least once a day. And it's easy done. You have here typical tools for, like this ball hub, which you should have on each slurry TBM site, a marsh filter, and that gives you good control possibilities for your slurry suspension. With an EPB TBM, it's a little bit easier, because at the end you have to monitor or you have to control how the material reacts with your excavated material. With the injection, you have different, you can adjust the foam to your material. You adjust this in the beginning, before you start with the EPB operation, you make practically those tests as already mentioned in a laboratory where you practically use different parameters and make a study with different amounts of water, with different additives, and as well with different volumes of air to find the best mixture of, for your EPB TBM operation. Later on during operation, practically you have to control what the outcome is out of the screw. You see on some TBM parameters, you can get quite a good idea how the material behaves and if anything is changing. EPB foam is one-off, so you inject it, you extract it, and it's lost. So you have not a quality problem, let's say, as you have with a bentonite slurry, which you pump back in and you circulate, and you have an aging there. So there it is more important with an EPB TBM to adjust it, to have the right foam generator sitting with the right parameters, inject it, you see how it comes out, how the TBM reacts, is easy flow, and then once it's out of the tunnel, that piece of foam is history anyway. So here again, the picture which I showed before. Filter cake for phase support pressure application. We have, of course, another effect in active phase support tunneling, and that's the time dependency. I mentioned before, you look here, with a slurry TBM, it is the way that the membrane is, by the rotation with the tools, it's scratched off the membrane every turn, and it has to rebuild by itself. So you have, at the end, quite a good definition of your membrane, of your size of the membrane during the operation of the TBM. You make a stop, you build the ring. Nothing happens, that's fine. You make a stop, you go home for the night. The suspension, the bentonite suspension, is still acting actively on your ground, on your tunnel face. And so over the time, it is actually able to penetrate then deeper into the tunnel face, indicated here with the blue section. What is happening then to your tunnel face? When we go back one step, you see here, what actually holds my tunnel face and stabilizes my tunnel face is here the pressure difference at the tunnel face between the surrounding ground and your active phase support pressure level inside the excavation chamber. It's in this, during advance, mentioned before, quite defined line. That's where your step is, and that's how you apply the phase support pressure. As it penetrates now into it, slowly, it has more time to penetrate, you see that the pressure gradient then is moving as well. So your front line is now here, it's not there anymore at the tunnel face, it's now a little bit deeper in. So your acting pressure difference is decreasing, it's getting smaller. So that was then over a night, but on Friday night you go for the weekend, it has even more time to penetrate. And so it grows further down. And with the growing, you see here that your pressure difference gets smaller and smaller. Everything is nice because the machine is silent, nobody's working, fine. Monday morning, the tunnel crews come into the tunnel, into the TBM, switch on the machines, start turning the cutter head, and at that moment they have the Monday morning collapse. It was in the 90s, beginning of the 90s, it was very common. Monday morning, it was always the same. The TBMs always had their one collapse. Until one paid a little bit more attention to this effect, and the experienced companies now have always their weekend mixture. So it's a very heavy, fresh, brand new heavy bentonite suspension which they pump in Friday evening to reduce this effect and to have practically the bentonite suspension not expanding that deep into the tunnel face. EPB TBMs have the same problem with time dependency. As you know, that is a mixture of the foam with the excavated material. All is during the advance in one rotation and turbulence, so the particles are distributed all over the tunnel face. If you stop then for any reason with the TBM advance, stop the cutter head, of course the material has time to segregate. So the heavier excavated material settles down, and your foam and the air especially just comes up to the top, and so you increasingly create here an air bubble. And at one point the air bubble is strong enough because enough air came up there and the pressure increases there, so it then penetrates into the surrounding ground, which it can do 70 times easier than water, and as a result you lose right away your face support pressure. That effect is actually happening on some projects where they are not even able to build a ring without turning the cutter head in the meantime in the front. So they cannot even stop for 30 minutes or 45 minutes without turning the cutter head in the front. So and that creates, of course, then a big problem. But they have then as well their special mixtures on Friday evenings. So, and yeah. So what you have to, first you have to prepare a good quality to generally apply the additional face support. And as well, you have to keep in mind that on special occasions, you need another step, a higher level of quality just to maintain a good status and to maintain, let's say, over weekend, a controlled tunnel face. What happens if you don't have as I mentioned before, at every TBM operations, you normally have some critical moments where you are about to lose the tunnel face, the active tunnel face support. You can have face collapses here. You can have, if it's a little bit more extreme, sinkholes. You can have blowouts. This is here right in the middle of a field with a bentonite suspension coming out, blowing out. And you can have as well then, due to your uncontrolled operation, excessive wear in your cutter head. Here another picture of standing two parties. That's when all the discussions start, of course, between contractor and client in front of a sinkhole. So what do? Common reflex is stop, have a meeting, shouting at each other, it's your fault, no, it's yours and stuff, and debate and do all things but not operating. The problem is then you have already a loose, because of this sinkhole, you have here in the front a relatively loose ground sitting there. That has not the properties anymore which you thought you have. So it's more sensitive to time dependency because the bentonite suspension in a loose ground area can, of course, penetrate a lot easier than it would have done into an in situ. So what happens is, if you discuss too long why it happened and what, you have a secondary collapse, which then might be even worse, because then it gets you inoperational. Because if you have a lot of volume coming in, then you have a problem, because you cannot turn on a lot of TBMs in the cutter head anymore. So our recommendation is then, of course, the better solution, if there's no real danger around, direct danger, then move the cutter head, go ahead, nothing is better for tunneling than advancing, and move the TBM out of that. Get up again into a controlled area. And when you are in the back with your tail shield, here you have a very good grouting system and pumping system. When that is then in this position, then you can stop and make an, let's say, an extensive grouting procedure just to stabilize this area. So that was as long as we have the TBM operational. We can have as well phase collapses where you cannot, as I mentioned, you just can't operate anymore. Out of obstacles, inside, too much material for the cutter head to turn, any reason, you don't know why, and you have to enter into this excavation chamber. But if you want to enter into the excavation chamber, you don't know what is expecting you. You want to go into the excavation chamber, if you open the door, you see it, but you don't know what is there waiting. So it's very difficult. So you try first to re-establish, let's say, a phase support system as well for the compressed air with different levels, I would say, of approach. The first one, is tried as well, is a lot using styrofoam. Styrofoam, put it into the suspension, pump it in. It will automatically go to the top because it's a lot lighter than bentonite suspension, and it's all up there and nothing at your face, so it doesn't help you at all. It doesn't block the loose ground in front, so you can build up pressure again. Sawdust or straw, people become very creative in those moments. That has been dumped as well into the bentonite suspension, pumped into the excavation chamber. It happens the same thing. It's lighter than the bentonite suspension. It swims up to the top in your cavity, and it doesn't help you for stabilizing the tunnel face, the rest of the tunnel face. Polyurethane foam. Very good. It actually works on occasions if the right foam is used, but you have a big problem afterwards because you inject it and it sticks to everything. It blocks your cutter head, it sticks to the disc, and it's terrible because it sticks very good. And you have to, before you want to tunnel again, you have to clean it out, and it creates really a lot of pain to the people, to the staff, to get it out under compressed air later. So what we would recommend is use large size polymers. Those are like we have in Germany, we have Gummibärchen. I don't know the English expression, sorry. It's jelly polymers, which you soak with water, and then you pump it with the bentonite suspension into the excavation chamber. It has more or less the same density as the bentonite suspension, so it actually swims wherever it is. It is everywhere. And that you can then actually approach and close the face with a loose ground. You can close that face and build up practically with that help a new layer, a new membrane, and to be able to change it then into compressed air mode. So it's typically, they are cheap, easy and quick to apply, sizes up to 20 millimeter square, not square, 20 millimeter each edge, and they work pretty well to stop, let's say, loose ground. The last stage is then the second stage is then use a sprayable membrane that has been developed now in the last years and has been used now for stabilization. That is especially the case when this before did not work, but you have the possibility to enter into the excavation chamber for a short time, but then you start losing too much air. And your air loss increases too fast. And when it's too fast, you get at the end of the capacity and you have to leave. So with a sprayable membrane, it is like a rubber, a rubber, a moment. I can show here, it's on top of ground. Here is thin layer with high tensile strength, and you practically spray and seal the complete tunnel face with that. And that works pretty efficient. You see here on the right-hand side an application with a very thin layer just applied here, and with that you stop immediately the air loss through that ground, and you get very quick your air loss down from excessive volumes. I have here just a very small film showing that. It's not. You see it here, it's applied with a normal air gun. You can have it here, that was like a toy really. You can even use it in shotcrete sizes as well. And with that, and then you practically go in as quick as possible. You start with the injection, with the spraying, and with that you have fast, practically sealed and secured the excavation chamber. So if that doesn't work, then we are at stage 3. That is one of the most critical levels, where we would then say, if you have situations like here, you are facing long stops because your tools are really worn down and damaged, and you practically need to refurbish your cutter head underground, which takes then a month of welding below ground. And you have here a very good connection to surface with your TBM, and here you see as soon as you start with compressed air, the compressed air is right there and bubbles out, and you just can't do but have no possibility to enter into the excavation chamber. There's one possibility to get control again of your tunnel face, and that's what we fill practically. We use artificial soil and fill practically from inside, from behind, from the bulkhead. We fill into the excavation chamber this artificial soil, and it's heavier than the bentonite suspension. So it practically fills up first the lower levels, and then you can practically pump with increasing pressure. You can fill it up to the surface and have practically the whole bentonite suspension exchanged against this artificial soil. This artificial soil will then harden up, and you can then manually excavate practically through that material. It's like a light binding concrete. That requires, of course, that you do tests, because the least what you want to do is you want to have a good concrete inside your excavation chamber, where you sit with a jackhammer and then try to free your TBM. So it must be really light, and you need to make these tests on site with the aggregates which are available, which takes 3 days or so typically, but then you are sure that you have a good mixture. Here's just a view. Opened the door with artificial soil. So that was the situation as you have seen before on the slide, where you practically had immediate connection to the surface. There it was completely sealed off. You had here open face, and you could even then start here excavating, hand excavating. This is just behind the cutter head here, and using hoists, and then you could start repairing your cutter head, changing the tools. So with that, it's a very controlled manner, and up to now, typically you get every TBM repaired under the worst conditions. So summary, understanding the face support model used, and to have an idea what the limitations are. That is a very important fact when you are starting with a certain phase support pressure, which you have received from an engineering company, that you practically know what it is about. Where are the limits? What are my flexibility within there? It's not a fixed value, it has a range. Tolerable phase support range should be calculated. As I said, not only for the lower limit, the higher limit is as well very important to know. Phase support failure might require swift action, and that should be done. It should be, it's not helping to wait and to discuss. If you have a loss in phase support pressure and you have a sinkhole or anything, move on if there's no danger. There are proven methods of gaining phase control during intervention. I showed you a couple of solutions. I'm sure there are more than that, but that are proven techniques. With that, thank you.